Product rule and the quotient rule for derivatives. Let's begin by talking about the product rule. So if we have a product of two differentiable functions, f of x and g of x, then their product is also differentiable. So as a reminder, differentiable functions mean a derivative exists. So here, if I have two functions that I can each individually differentiate, that I can multiply them together and differentiate their product using the product rule. Now what the product rule says is when I take the product of those two functions, so here we have f of x times g of x, and we're applying the derivative to that product. So this d over dx is our operator that means take the derivative of what's in parentheses here. The product rule says we'll take the derivative of f of x first, so that would be our f prime of x, keep the second function, or g of x, the same, plus we then will keep f of x the same, times the derivative of g of x, which would be g prime. So again, we take the derivative of one function, keep the other function the same, plus we then reverse it, keep the first function f of x the same here, times the derivative of g of x. Let's go through a couple examples. So in example 1, we have the function y equals x cubed minus 19x times 2x to the 16th plus 4x squared minus 100. Here we have a product of two functions. Our first function here is the x cubed function, and then our second function is this 2x to the 16th plus 4x squared minus 100. We have the product of these two, so we're going to use the product rule here to take this derivative. So I'm going to start by using the same notation that is applied to me in the problem. So I want to find dy over dx, so I'm going to go ahead and label my derivative as dy over dx. And the way the product rule works is we take the derivative of the first function. Using the power rule, our derivative here would be 3x squared minus 19. Now I'm putting this whole thing in parentheses because I need to multiply this by the original second function. So I'm going to keep the 2x to the 16th plus 4x squared minus 100 the same. So here down below, if I were to label these, this would be like my f prime, and this would be my g. So I took the derivative of the first function, kept the second function the same, plus I'm now going to keep the first function the same. So the x cubed minus 19x, that would be our f, times I now am going to differentiate the 2x to the 16th function. And that would give us 32x to the 15th using the power rule, plus 8x, and then we know the derivative of any constant would drop to 0. So that would be the end of our derivative here of g, or our g prime. I've got to make sure I'm putting every one of these functions here in parentheses because I want to make sure I take the entire derivative of f times the entire original function g plus our entire f here times our g prime. Now, of course, we could avoid the product rule and multiply all of this out, but that would be a lot to multiply out. And as functions get more complicated and we involve stuff like trig functions or exponentials or logs, there's actually no way around foiling stuff out. If I have x times, let's say, cosine of x, I'd be forced to use a product rule in that scenario. So although today all the examples we're going to see, you could just multiply out first and then apply the power rule, we're going to go ahead and apply the product rule to each one of these. Okay, in our second example here, we want to find f prime for this product of functions. So our first function here is 3x to the 5th minus 4 times the square root of x times our second function here is going to be 15x plus 6x to the 4th minus x to the 19th. And we want to find f prime for this. Now, notice a couple of things. I can use the power rule on most of these terms, but this 4 times the square root of x first needs to be rewritten. So I'm going to go ahead in my first step here and just rewrite the original function. So I'm going to make it equal to f of x since I am not taking a derivative here, I'm just rewriting. And using algebra, we know that we can rewrite 4 times the square root of x as 4 times x to the 1/2 power. And then the rest of these would all stay the same. So we still have 6x to the 4th and then minus x to the 19th. Okay, now applying our product rule here, f prime of x, let me actually scoot this up because we are going to simplify our answer a little bit. So I want to have enough space for two lines here. So f prime of x using the product rule says take the derivative of the first function. So our derivative of 3x to the 5th would be 15x to the 4th minus, when we take the derivative of 4 times x to the 1/2, Using the power rule, the 1/2 will come down. 4 times a half would give us 2. And then we'll get x to now the negative 1/2 from doing 1/2 minus 1 in that power rule. There's our derivative of our first function. I'm now going to rewrite the second function because I'm not taking the derivative here. This would just be our g. So I want to keep the second function the same. Plus, now I want to keep the first function the same. So I'm going to put all of that in parentheses, and I could use the x to the 1/2 or the square root. Now times, I'm now going to differentiate our second function. So using the power rule, derivative of 15x would give us 15, plus derivative of 6x to the 4th would give us 24x to the 3rd, minus derivative of x to the 19th would be 19x to the 18th, all using the power rule. Now there's a little bit of simplification I can do with this x to the negative 1/2 exponent. So I'm going to go ahead and rewrite that in case I have a multiple choice question. I'm trying to make it match one of the options. So that can get rewritten as negative 2 over x to the 1/2, or I can even make that a square root of x. And then the rest of this I'm going to rewrite the exact same because there's nothing else I can do to simplify those terms. I just want to make sure that I've got my derivative of f here in parentheses times my second function, plus the first function here of f of x stays the same, times the derivative of the second function here. And each one of those ends up in parentheses. And there would be our derivative of f. Now let's look at our third and fourth examples here. So in our third example, we want to find dy over dx, which is the derivative of y with respect to x, for this product of functions. Just like in our prior example, there's a little bit of rewriting that we can do in order to use the power rule. So I'm going to rewrite the original function. So again, this is still y, I'm not taking a derivative here. I'd still have pi squared minus 17x. Now plus 9 over x to the second, I can't use the power rule when I have variables in my denominator, so I need to rewrite that as 9 times x to the negative second. And then the second function is all good to go to use the power rule as soon as we need to. So I'm going to just rewrite that second function. Oops, that should be a parenthesis. There we go. So now to find dy over dx, we're going to need to use the product rule since we have a product of two functions. So in the product rule, we want to take the derivative of the first function here. That'd be the pi squared minus 17x plus 9x to the negative second. Why don't you guys pause the video here and try to find the derivative of this first piece on your own first. Okay, to find the derivative of this first function here, now pi squared, it looks really tempting to want to make that a 2 pi, but remember pi is a constant already, and if I take a constant or a number and I square it, I still have a number. Derivative of any constant would drop to 0, so the derivative of pi squared will be 0, minus the derivative of our next term would be negative 17, minus derivative of 9x to the negative second. The reason I wrote a minus is when the negative 2 comes down, that's going to become a negative 18, and then we're going to end up with x to the negative third because we have to subtract 1 off. Now in the product rule, we took the derivative of the first function. We're going to rewrite the second function since we are keeping that second function the same. Plus, we are now going to rewrite the first function. So I'm going to still have the pi squared 17x plus, I could write this as either 9 over x squared or 9x to the negative second, times, now we want to take the derivative of the second function. And on the second function, you can use the power rule. Why don't you guys pause the video and find the derivative of this 4x to the 7th piece. Now the derivative of that, using the power rule, would be 28 x to the 6th plus 60 x to the 4th minus 11. And we have now differentiated our original function y. I'm going to just go ahead and clean up our final answer just by getting rid of this negative exponent and rewriting this. So this is still my derivative, this is still dy over dx. I'm just doing a little bit of algebraic simplification here. So we're going to end up with negative 17 minus 18 over x to the third times 4x to the 7th plus 12x to the 5th minus 11x plus our pi squared minus 17x plus 9 over x squared times our derivative of our second function. And again, just to annotate and kind of point out where all these pieces are coming from, this first piece here again would be the derivative of our first function here. So the pi squared minus 17x plus 9 over x squared. And then the next piece is keeping the original second function here the same. Plus, we then keep the first function the same. So I've rewritten that whole pi squared function times the derivative of the 4x to the 7th plus 12x to the 5th minus 11x function. So I've got my original times, the derivative of the first times the second, plus the original first times the derivative of the second. Okay, let's do one more product rule. Here, g of x is going to be 10x to the 14th minus 6x squared minus the cube root of x to the 21st times 3 over x to the 8th plus 5x to the 4th minus e times x squared. And we want to go ahead and find g prime. Now, in order to use the product rule here, I'm going to need to take each derivative individually, and some of these terms I'm going to need to rewrite before I can use the power rule on them. So my first step here is I'm going to just rewrite my original function g. So notice I'm not calling this g prime. This is still the original function g. 10x to the 14th I can take the power rule of, so that piece is already good. Same thing with the 6x squared. But this cube root of x to the 21st, now is kind of a little recall over here. The cube root of x would be x to the 1/3, but since I have x to the 21st, then when I rewrite that, I have x to the 21st all to the 1/3. Oops. Now, using properties of exponents, we could actually simplify this down. And how could we simplify down x to the 21st all to the 1/3? We can multiply the exponents there since we have power to power, and that would end up giving us x to the 21st over 3 from the times 1/3, which would give us x to the 7th. So this piece is really just x to the 7th in disguise. Times this 3 over x to the 8th, I can rewrite as a negative exponent, and then the rest of this is already ready to go. So I'm going to just go ahead and rewrite that with our rewritten form of g of x. Now from here, we want to find g prime. Since I have a product of two functions, I've got to use the product rule. Why don't you guys pause the video here and find g prime, for example, 4 on your own first. Okay, using the product rule, I want to take the derivative of the first function. So our derivative of 10x to the 14th would give me 140 x to the 13th minus our derivative of the next term would be 12x minus the 7x to the 6th. So that first piece right there is the derivative of the first function. Now times, I want to keep the second function the same. To save myself space, I'm going to rewrite that as a fraction since I'm not taking a derivative here. Plus, I want to keep now the first function the same. So 10x to the 14th again, minus 6x squared, minus, I can go ahead and write that as x to the 7th to save a little space. I could also rewrite as the cube root, again, of x to the 21st since they're equivalent, times, now I want to take the derivative of my second function. So using the power rule, that will give us negative 24 x to the negative 9th, because we've got to subtract 1, plus 20x to the 3rd. And then e here is a scalar on x squared, so it's going to go along for the ride, and we'll get negative 2e times x using the power rule. That there would be our derivative, and if we just want to rewrite some of these negative exponents, we could do that. And kind of a little bit of a simplified form of our final answer here would be 140 times x to the 13th minus 12x minus 7x to the 6th. That was all of our derivative of the first function times the original second function plus, now I would again rewriting my first function. And now in our derivative of our second function, the most I can do is just rewrite that x to the 9th back down in the denominator, and it will become x to the positive 9th, then plus 20x to the 3rd minus 2e times x. And that would be kind of our more simplified form of our derivative. Now, of course, on any of these, we could then multiply everything out and try to combine like terms, but the purpose here is that we're just practicing how to do the product rule, and I want to minimize too much algebra simplification we need to do, just doing the little ones like the negative exponents or the radicals that we can rewrite. Okay, our second rule that we're going to talk about in this video has to do with what happens when I now have a quotient of functions. So we dealt with when I have a product of functions, but now we're going to see what happens if I have a quotient of two functions. So here, this time, we have our derivative of f of x in our numerator over g of x is going to be our denominator function. So since f of x and g of x are differentiable, then I can take the derivative of their quotient. I do have one assumption here that g of x can't be 0, because we know that we cannot divide by 0. But according to the product rule, when we take the derivative of our quotient here of f of x over g of x, we take the original denominator here, so I have g of x as is, times the derivative of the numerator, this would be f prime, minus the original numerator here, f of x, times the derivative of the bottom, which would be g prime, all over, so that whole subtraction is over the original function of the denominator squared. Now, one thing to take note of with a quotient rule is because of that subtraction sign, there's not too many other ways that we could rewrite this. In the product rule, we had addition and multiplication, which are both commutative, but here with this subtraction, it makes a huge difference to make sure that our first product here is the denominator times the derivative of the top minus the top function times the derivative of the bottom, all over the original bottom function squared. Now, there's kind of some acronyms that you can work to help with memorizing this, and one of them that I use is if I name the top function here the high function for being in the numerator, and the bottom function here the low function for being in the denominator, I would say that I get the low function times d high, meaning the derivative of the top function, minus the top function minus high times the derivative of the bottom, or d low. So low d high minus high d low, all over low squared, the bottom function squared. And if that helps you with memorizing the quotient rule, great. If not, then maybe it'll help somebody else. So again, low d high minus high d low, all over low squared. Let's go ahead and do some examples here. So in our first example, we have the function 14x squared minus 18x plus 22, all over 3x to the 11th minus 5x. And we want to go ahead and find the derivative of this. So I'm going to start my derivative way over here just to make sure I have enough space. So I'm finding dy over dx. Now the quotient rule already deals with the fraction. So I'm going to go ahead and just write the gigantic fraction bar that we're going to need. And we now start with the original denominator. So that would be g of x. So I have 3x to the 11th minus 5x that I'm just going to go ahead and rewrite, times I now need to find the derivative of the top. So the derivative of our numerator here, we can use the power rule. We'd get 28x minus 18 minus, now I want the original numerator, 14x squared minus 18x plus 22, times, I now want to take the derivative of the denominator, and again, I'm going to use the power rule. So I'm going to get 33x to the 10th minus 5. And all of that is in the numerator, so I got to make sure to extend my division bar there. Then that whole thing gets divided by the original denominator, so 3x to the 11th minus 5. That whole function, so I need to put in parentheses, squared. So I've got to be very careful with parentheses on both the product and the quotient rule, but I got to make sure I have my bottom function, so low times d high, derivative of the top, minus the high function times the d low, derivative of the bottom, all over low squared, or the bottom function squared. There. And that would be our quotient rule. Again, we could multiply out, try to combine like terms, but the idea here is that we just want to practice the product in the quotient rule. Let's go ahead and look at example number 6. So here, h of x is equal to x to the 12th plus 6x squared, all over 7x to the 5th minus the 8th root of x plus 1. Now, similar to some of the examples we saw with the product rule, we're going to need to first rewrite the original function so that we can use the power rule on each of these individual derivatives. So in the numerator, I don't need to rewrite anything there. And in the denominator, the only piece that we need to worry about is that 8th root of x. Well, we can rewrite that as x to the 1/8th power, and then we still have that plus 1. Okay, let's go ahead and find our derivative here. So the problem called it h prime, so I'm going to go ahead and label my answer as h prime. Again, gigantic fraction that we're going to end up with. And in the quotient rule, we take the bottom function, so that's the 7x to the 5th minus, I'm going to rewrite it as the 8th root of x to save a little bit of space, plus 1, times the derivative of the top. So using the power rule, we'll get 12x to the 11th plus 12x minus the original top function, so that's the x to the 12th plus 6x squared, times the derivative of the denominator. So using the power rule here, we'd get 35x to the 4th minus 1/8 x to now the -7/8, because remember I've got to subtract 1, and 1/8 minus 8/8 would give me -7/8. And then the derivative of 1 would drop to 0, so that is the end of my derivative of the denominator, all over the entire denominator. So I've got to make sure that that whole function there is in parentheses squared. Now we could rewrite the x to the -7/8 as 1/8 times x to the +7/8, but for the sake of space, I'm just going to go ahead and leave that. Okay, let's look at our last two examples here. So in example 7, we have k of x is 20 times the 4th root of x plus x to the 27th, all over 54 minus 3x to the 5th plus x to the 15th, and we want to go ahead and find the derivative. Now, similar to the last example, I do need to do a little bit of rewriting just to make sure that I can use the power rule easily enough. So up here on the top, I'm just going to rewrite k of x. I could rewrite that 4th root as 20x to the 1/4 plus I still have x to the 27th all over the denominator. There's nothing there that we can rewrite with that, so I'll just recopy it over. Okay, let's find our derivative here. So because I have a quotient of two functions, I'm going to need to use the quotient rule. So we take the original denominator, so this would be our low function, times d high, or the derivative of the top function. So using the power rule, the 1/4 would come down. 20 times 1/4 would actually give us 5, and then we end up with x to the -3/4 by subtracting off 1 from 1/4, plus 27x to the 26th power. So we have low d high minus high, the high function, the original numerator. I'll do that as x to the 1/4, x to the 27th, there we go. So low d high minus high, and then derivative of the denominator. 54 is a constant, so that would just drop out. Then using the power rule, we'll get -15 x to the 4th plus 15 x to the 14th. All of that is the derivative of the denominator, all divided by, that entire difference is over the original denominator. So 54 minus 3x to the 5th plus x to the 15th, that entire denominator squared. So again, make sure I've got parentheses on the whole thing, not just accidentally on the last term there. Okay, let's look at our last example. We want to find y prime for the function y equals x to the 8th plus 10x to the 3/2 minus 5x all over 10x to the 9th minus 4x to the 7th plus 30. Why don't you guys pause the video here and find this derivative on your own first, and then we'll check it together. Okay, to check our derivative here, I'm going to use the notation y prime since that's what was provided for me in the problem to represent our derivative. I have a fraction, so I have a quotient of two functions, so I need to use the quotient rule. The quotient rule says I take the original denominator, so that would be the low function. So I'm going to recopy that down. Times, so all of that is in parentheses, times now in parentheses the derivative of the top function. So that would be 8x to the 7th using the power rule, plus when I bring down the 3/2, 10 times 3 divided by 2 would give me 15. And then we'll get x to now the positive 1/2, because 3/2 minus 1 would give me 1/2, minus 5. So So I've got low times d high minus high, the original function. So I'm going to rewrite all of that out. Times d low, the derivative of the denominator. Using the power rule, we'll get 90 x to the 8th minus 28 x to the 6th. And then the derivative of 30 would drop out to be 0. All of that is divided by the original denominator. So no derivative here. I'm just recopying down the original denominator. But that whole function squared. So again, I've got low d high minus high d low all over low squared. Or the original denominator times the derivative of the top minus the original numerator times the derivative of the denominator, all over the original denominator squared. And that would be our quotient rule. So the product and the quotient rule right now we're just seeing with what we call algebraic functions, but as you progress forward you're going to end up seeing the product and the quotient rule with also trig functions, exponentials, log, and maybe some inverse trig functions as well.